Okay, so welcome back to part three of our lecture on confidence intervals. I have basically an R demo that I want to present to you on how to actually calculate confidence interval for real data, which is what most of this bit of the lecture is going to be about. But before I get into that, I wanted to go back and just make one or two points about confidence intervals in general and kind of the mechanism we use to calculate them. So for that, we can go back to this sort of sample confidence interval that I wound up calculating at the very end of the second part of the lecture. So if you might recall, hopefully, we had this population distribution with an underlying mean of 5, and then its standard deviation was 0.2. When we took a sample from that, a theoretical sample from that population distribution, we said, well, that mean of that sample is 5.2. So our actual confidence interval is shifted a little bit over to the right on this graph from where we know from our sort of God's eye view where the population mean is. It's shifted over here between the values of 4.8 and 5.6. And then, luckily, the population mean winds up being within that interval, but it doesn't have to. It just usually it will if we're estimating it with a 95% confidence interval. And so what I want to focus on here is sort of this bit that gives us that 95% confidence interval, which we call the margin of error. So it's plus minus 1.96 times the sample standard deviation divided by the square root of the number of items in the sample. So it's this part based on the equation that we used to calculate it. And this is what it's equal to in general. Just the part that's kind of interesting here that I wanted to focus on for a bit is this sample standard deviation S divided by the square root of n, or the number of items in the sample. And that part we said is called the standard error, which also happens to be the standard deviation of the sampling distribution. So there's kind of a lot of things that are kind of being conflated into one here, but just to kind of hopefully clarify where some of this terminology comes from. And I'll preface this again by saying I'm not actually a statistician. I don't know all the history of this, but this thing is called, this bit here is called the standard error. And this combination is called the margin of error. And this 1.96 multiplier just can change depending on what we make the percentage for our confidence interval. In this particular case, it's 95%. So for that reason, we're multiplying this whole this standard error, this part, by 1.96. That gives us 95% of the sampling distribution. But kind of the terminological connection there is between the margin of error and the standard error. So you can maybe think, we call this bit just by itself the standard error. And if we were just going to multiply it by 1, that would be basically 1 standard deviation of the sampling distribution rather than multiplying it by 1.96. So in the same sense, like when we converted a normal distribution to a standard normal distribution, we converted basically all of its values to z-scores rather than whatever the raw data was. You can think of the standard error as being just sort of like 1 unit of margin of error as opposed to like 1.96 units of a margin of error. And so the part I think that can often be confusing if you're like me or a lot of beginning students is like, this thing is called the standard deviation for a normal distribution, but then all of a sudden when we get to the sampling distributions, it's called the standard error, rather than like the standard deviation of the sampling distribution, which is also what it is. But I think the idea there is that we're using that kind of entity primarily to sort of make these estimates for confidence interval purposes. So this bit factors into, if I can get it highlighted, this bit factors into these calculations depending on how big we want to make the confidence interval, but that's kind of like the primary unit of error in our guess as to where the population mean might be, because this is what we're adding or subtracting to our sample mean to make a guess about where the population mean is. And I kind of wound up talking about that a little bit more than I wanted to, but maybe that makes it a little bit clear that we're thinking about the standard deviation, the sampling distribution, primarily so we can make estimates about the population mean or parameters of the population itself. And this word error is kind of how we're making that connection clear. I'm not going to say anything more about that in case I made it less clear for you, but I will give you some examples of actual confidence intervals, which you might be interested in, as I am interested in. And it's currently relevant because I grabbed these numbers today off of Alberta Health's COVID-19 webpage. And here's the link where I got these guys from. And these are confidence intervals. They're going to be calculated in a different way, but it's the same general idea. And what they're trying to estimate here is the vaccine effectiveness against the coronavirus for various vaccines. So what they give you is numbers for 3 different vaccines. And what the numbers they're giving you is what they call vaccine effectiveness. And I think what that means is if you've had the vaccine, what are the chances that you will not get sick with the coronavirus, or you will not get a documented coronavirus infection. So to give you one example of sort of a well-functioning vaccine, the Moderna vaccine, 81% of the people who've had 1 dose have not gotten a coronavirus infection as far as we know, and then 92% who have gotten 2 doses have not gotten a coronavirus infection. So, I mean, we already know this hopefully that, but like even if you're fully vaccinated, it's not 100%, right? Life isn't perfect. So you might still get a coronavirus infection, but normally it doesn't lead to something horrible for you health-wise if you do, because the vaccine still provides some protection in that case, but it doesn't work 100% all the time. And the point I kind of wanted to make here, which is nice, is that they're also giving 95% confidence intervals. So, you know, like I said, this is a guess. Like for Moderna, the guess is that for the whole population of people in Alberta who've had the Moderna vaccine, 81% of them will not get sick with the coronavirus if they've only had 1 dose of the vaccine. But that might not be the actual population mean. It might be somewhere a bit off from that. But the 90% confidence interval is actually pretty tight here. It's 80 to 82%. So we can be fairly confident that it's within this range. But, you know, it might be 85 or 72 or something like that. We don't know absolutely for sure, but this is a pretty good guess. So they're presenting this statistical information on top of these overall numbers. And then they also are presenting vaccine effectiveness against the various variants of the virus that have emerged over time, and kind of doing it in a bit of a funny way because they're mentioning, say, like the UK variant or the Brazilian variant, even though my sense is that it's not considered PC at this point to sort of associate these variants with specific countries, because it's not like the people there can be blamed for this sort of thing or anything like that. But then they also have this B1617 variant, which is commonly known as the Delta variant, which is the one that's really spreading quickly around everywhere. So, and that's the one that the vaccines are not super great against, especially if you only had 1 dose. And you can see that number jump out here for this column and slightly more subtly over here. But generally speaking, for fully vaccinated people, the vaccines are doing pretty well against all the variants, and it doesn't really matter which one you've got, at least amongst these 3, which is nice to hear, or nice to see. But yeah, we still got a ways to go to kind of get our world back to normal, if we ever will, with the vaccine. And part of the way we can do that is by learning through stats how effective these various approaches are. Right? And hopefully this helps this make a little bit more sense in your everyday life. And one other way I'm going to help, or try to help it make more sense, is by walking you through an example of how to calculate these things using R. So I want to give this a try for the F0 data that we've looked at before. And normally when I do this in class, I have everybody in class calculate a confidence interval. And the reason I do that is because everybody's confidence interval will or will not include the population mean. We're going to kind of like state what the population mean is before we run through the demo, and then we find out whether, you know, your confidence interval includes the population mean or not. And usually we'll find that if we calculate 95% confidence intervals for everybody, then 95% of the time people's confidence intervals will include the mean, and then 5% of the time they won't. We don't have the luxury of being able to do this through YouTube on the internet with videos, because I'm the only one here at the moment. but you can try this process at home as you're watching this, and you can see whether or not your confidence interval includes that population mean. We'll see what happens with mine. I think I might do it twice, and then, maybe it will, maybe it won't. So I'm going to do it first with a sample of 9 observations, and then again with samples of 81 observations, and we'll see how well it works. But at the very least, hopefully you'll get a sense of how the method works. And then the question is, will everybody's samples produce confidence intervals that include the actual population mean? And then we can also try it with 50% confidence intervals, and then we'll think a little bit about what that means by the time we get there. So I'm going to set that one aside for the moment and just show you how this works for a 95% confidence interval. And I've got the R commands already up here on the PowerPoint. This is using F0 data from my 2018 class for whatever that's worth. So I collect this data for every single class, and then, these examples become slightly different each time around. But there's a lot of data in here from a variety of different speakers, both male and female. We've seen this sort of thing before. And what I want to look at, this is the summary that's loaded up. There's an F0 column here, and this already tells me in the summary command what the mean is. But in case you have forgotten or need a reminder, we can actually calculate the mean this way. Luckily for us, it winds up being basically the same as what it says here. It's 190.67 basically. And so what I'm going to do is grab a sample of 9 observations. So that's the 9 here, just 9 at random. But there's no replacement here, so there are 9 different rows out of the F0 data. And I'm going to pump those into a sample vector that I'm calling S9. And it looks like that, right? So again, this is from a variety of different speakers, and the F0s are kind of all across the board here. What does that mean? Or at least what is the mean of this sample? Who cares what it means? If we know the mean, all we need to know is that it's 274.6. Okay, so we can kind of draw an analogy here with what we're doing from what we did before. So back here, we talked about like the population distribution. And remember, this is F0, so the population distribution is not going to be normal. It's going to be skewed one way or the other. Our sampling distribution should be normal, though, if we have large enough N in the samples. But what we're getting is like a population distribution mean of like 190. And then our sample mean, this little dot here, in this particular case, is 274, which doesn't seem that close to 190. So maybe we will get a confidence interval that includes the population mean. Maybe we won't. I'm doing this anew every single time, so there's no guarantees, right? The same thing is true when you run an experiment. You might be surprised by your results. We also need to calculate the standard deviation of our sample. It's just the standard deviation of these 9 numbers right here. And I mentioned this before, but we're just going to make a guess or assume that the standard deviation of these 9 items is going to be basically the same as the population standard deviation. And that's not necessarily the case. And in fact, we can do a quick check to see how similar they are by looking at the standard deviation of just the F0 from the entire population, so-called. So that is 102, and from our sample, it's 175. But remember that in a real experiment, you're not going to know this mean of the population. You're not going to know that at all. You're not going to know the standard deviation of the population at all. You're going to know these 2 numbers, and on the basis of these 2 numbers, you're going to try to guess what this mean is. And part of that process involves assuming that this number is the same thing as this number, even though there's no way to know that, and there's no way you can prove it. It's just a reasonable guess. Okay, so from there, we try to figure out what the standard error is. The standard error is the standard deviation of the sample divided by the square root of the number of observations in the sample. So I'm going to pump this into a variable called SE for standard error. And you don't really need to make this explicit, as we'll see on the next slide, but this, just to show you what's happening here, is that I'm taking this value, which is 175 up here, and I'm going to divide it by the square root of n, which is the square root of 9, or 3, right? So 175 divided by 3 should be about like 58 or something. Yeah, and there it is. It's like 58.38, so on and so forth. That's the standard deviation of my sampling distribution. It's narrower, right, than the standard deviation of the population or the standard deviation of the sample itself. Okay, and we've seen this before again already today in this video, but here's how I'm going to calculate what the confidence interval is. The 95% confidence interval is equal to the mean of the sample plus 1.96 times the standard error. However, this is a bit of a simplification, and we've seen this before when we talked about z-scores and the proportions of normal distributions and whatnot. But the 1.96 is an approximation, and there's a better way that we can calculate that value, and it's in R we can do it using the Qnorm command. So I'm going to just show you how this works here and kind of link it back up to the equation we saw a second ago. But sort of the upper limit of our confidence interval is going to be the mean of our sample. This is X bar right here. Maybe it'll be better if I do it this way. So this is the upper limit of the confidence interval. This is X bar. Sorry, I can't just get that part by itself somehow. This is X bar, as we see like over here. And then we have the standard error bit over here at the tail end of the equation. We just calculated that a second ago. And what I'm doing a little bit differently here with the R command is not multiplying that standard error by 1.96. Instead, I'm multiplying it by Qnorm of 0.975. So that's giving me basically a z-score that's appropriate for that proportion of the distribution, that proportion of the normal distribution. And it's going to have 97.5% of the distribution to the left of it, basically. So to get the lower limit, I do basically the exact same thing by using the Qnorm command again. But in this particular case, I'm going to subtract that value. So the only thing that's changing between these two equations is that plus is going to a minus down here. And this is going to give me basically the left-hand side of the interval, multiplying Qnorm of 0.975 times the standard error in this particular case. So I'm actually going to do this. And if you have been following along on the internet, you should do it too. If you've been following along in class, you should do it as well. And we'll find out if we get the population mean within our confidence interval. What do you think? Let's remind ourselves of what that population mean is, that so-called population mean of the entire F0 sample. That's all the F0s that are collected, at least, from this class. We can look at the upper limit by just typing upper limit. 389. Okay, lower limit, it's got to be under 190. It is 160. Okay, so here's our confidence interval. We are 95% confident that the population mean is between 160 hertz and 389 hertz. And it is. But we don't know that if we're actually going to run this experiment. We just put it out there that we'd say, oh, our confidence interval is that the mean is between these two numbers. It's the exact same thing basically as Alberta Health saying, well, the mean is somewhere between 58 and 63%. Okay, but we don't know in reality where that mean exactly is. It's just probably there. Yeah, and in this particular case, we know that it is, which is nice. But sometimes it might not be, just 5% of the time. It won't be because we've established that this is a 95% confidence interval. Yeah, so let's try it again, and we'll see if we get anything different. So by trying it again, all I'm going to do is run the experiment again, so-called, by taking a different sample of 9 rows of the F0 data. Yeah, so we look at this again, slightly different numbers. What happens? Yeah, we don't need to do that. I think we just need to do this. Right, so let's calculate the upper limit again. S9 has changed, but doesn't matter to R what happened there. And if we look at the upper limit, it's 292. If we look at the lower limit, it is 137. So we still luckily have the mean within that confidence interval. We just have a different confidence interval. Yeah, and this is also something we're thinking about, like in terms of F0, you're presenting your data at a conference or whatever, and you're saying, well, I took a sample of like 9 F0 measurements from my group of speakers, and I found out from that the F0 is probably between 137 hertz and 292 hertz. And some people, some knowing phoneticians out there might look at that and say, that's not really that accurate, because there's a big wide range between the lower end of that limit and the upper end of that limit, or upper end of that interval. It's sort of like going here to the vaccine numbers and saying, well, AstraZeneca is 61% effective, but the confidence interval is like 27% to 92%. So anywhere in there, maybe. It's sort of not all that convincing if your confidence interval is that broad. Because you want to be 95%, you want to be right 95% of the time. And sometimes to do that, you have to put, a bigger guess out there. So in this case, both times we did have the population mean within that interval, but they're fairly big intervals. So let's try it in a slightly different way. Let's try it with a sample size of 81 observations and see how that changes things. So in this case, I'm going to go up here and change this number to 81 and change that number to 81. And I'm kind of doing this just to make the math a little bit easier, because the square root of 9 is 3, the square root of 81 is 9. It's sort of like we're just squaring our way up. And having done that, I need to calculate new upper and lower limits for a new confidence interval. The population mean is not changing here at all. Just keep that in mind. We have the same underlying population, but I'm taking a bigger sample from it. And in doing that, we'll see what our upper and lower limits look like for our confidence interval. Still a 95% confidence interval. The only thing that's changed is this number 81. So instead of basically, since I divided in the first case by square root of 9, which is 3. And now in the second case, I'm dividing by square root of 81, which is 9. The standard deviation of that sampling distribution should be a third as wide, right? So we should have a much narrower confidence interval in this particular case. And we do. So in this case, our lower limit is 173. Our upper limit is 215. We know that the population mean is 190.67, whatever. We didn't look at this, but we can take a look at what the mean of the sample is 194. Generally speaking, this is going to be true. Like the more items that are in your sample, the bigger your n is, the more accurate your mean is going to be, the closer it will be to the population mean. Not always, but usually. And then also, if you calculate confidence intervals on the basis of that, your confidence intervals should be narrower. They should be giving you basically a more accurate estimate of what that population mean is. I get a more precise estimate of what that population mean is. The accuracy is not going to change. You're going to be correct 95% of the time no matter what, but you're going to get a narrower interval in that case. Sorry. Physicists all over the internet are just screaming and tearing out their hair at the things I'm saying. Sorry, I'm not perfect either, just like life itself. Okay, lastly, let's try an exercise where we calculate the 50% confidence interval for a sample of 9 observations. And so let's think about this. So I've still got, we'll keep the same S9. And actually, let's go back and remind ourselves of let's do it this way. So I'm going to keep that sample of 9 and store it in differently named variables for my confidence interval. So this was a relatively big one. It still included the population mean, but it was from 137 to 292. And so what I want to change here is not the sample itself, but just the percentage of the confidence interval. So the way I'm going to do that, hopefully you can see this, or see it before I do it, but I'm going to change this number within the Qnorm function here, that part of the equation. So I'm going to add to my sample mean the standard error times Qnorm of 0.75. And this is kind of the crucial part here, because if the added part has 75% of the proportion to the left of it, and then the lower part has 25% of the proportion to the left of it, I'm going to get 50% in the middle, which will give me my confidence interval, my 50% confidence interval. So let's do the other half of this. The only thing that changes is that plus to a minus. And I get my lower limit that way. What does it look like? Oops, I shouldn't have overwritten the first one, but it doesn't really matter. My upper limit is 241. My lower limit is 188. So kind of lucky in this case that the lower limit does include, or sorry, this confidence interval does include the mean, the population mean of 190, wherever it was. 190.67 is within this interval. This is from 188 to 241. So yeah, it's, in that case, happens to be accurate, but kind of, again, this is another way to make your interval a little bit more precise. So when we looked at the 95% confidence interval, is pretty broad. It was from 137 to 292. If I make the percentage of the confidence interval smaller, that also makes my range of estimates for the population mean smaller as well. The range of the confidence interval itself gets smaller too. And that's because it winds up being less accurate. It's only right 50% of the time. So let's take another sample and calculate another 50% confidence interval and just see what happens. So we're going to get another S9 and we'll calculate the upper limit that way and the lower limit that way. And now we will see, no idea what's in here. It doesn't look good. My 50% confidence interval in this case is from 141 to 164, and that does not include 190. And this is kind of what you'd expect based on the odds or the basic percentage of the confidence interval itself. For every time you get the population mean within your confidence interval, you should get another time where it's not in the confidence interval. Half the time you're right, half the time you're wrong. That's what 50% confidence means. Okay, so hopefully that makes sense. Again, the only thing that's changing here is this number in the Qnorm function. I'm not going to say anything more about it, but I will give you a few sort of caveats or criteria to think about when you're using this method. And again, we have this joke. I can't remember if I've said it in the videos so far already, but nobody dies if a linguist is wrong, right? But you might die if your health professional is wrong. So for that reason, or that's maybe one of many reasons why, Alberta Health wants to put out accurate estimates of things like vaccine effectiveness or whatnot. In linguistics, we don't often estimate parameters like that, but in case you do, you might want to keep these things in mind. And these are criteria or caveats that I borrowed from the Introduction to the Practice of Statistics textbook. This is what you need to keep in mind in order to use this technique meaningfully and successfully. So number one is this sort of sampling ideal, that your data must be from a simple random sample of the population. It can't be biased in whatever particular way. And remember, that's an ideal we don't often meet, but it's one that should be in place for this to work as it's designed. Number two, inference cannot rescue badly produced data. And this is going to be true across the board for everything we do from here on out through the rest of the semester. Make sure you design your study well to begin with, and then you can run meaningful stats on it afterwards. And we're going to get into sort of more and more sophisticated inferences as we go. This is just kind of the start. Number three, confidence intervals are not resistant outliers, because remember, we're estimating where the mean of the population is, and means can be, shoved one way or another by outlying values. We've talked about that before, because this is the mean we're talking about, not the medians, so on and so forth. So that can be problematic. If n is small, like less than 15 or so, and the population is not normal, the true confidence level will be different. So, oftentimes people will ask me, like, well, how many subjects should I run in my experiment? And I often just give them as a rule of thumb, like, well, 20 sounds good. And what you don't want is a really small n if you can avoid it, like less than 15, because that complicates the stats as well. That will make it harder for sort of this central limit theorem to kind of kick in and convert your non-normally distributed underlying data into like a normally distributed sampling distribution. And then, I can't even get into what consequences there are for the stats there because I don't really understand them, but I know it's just going to be problematic. Number five, there's some guesswork involved in estimating the population standard deviation, the sigma, from the sample standard deviation, the S, and I've shown you that as well in our little demo. that's an assumption you make, which is not necessarily always going to be true, but hopefully it will be true if you want to be able to get this to work. Okay, not going to say anything further about that, but I will give you sort of the moral of the story, which is that you need to keep in mind these theoretical assumptions that went into the process of calculating the confidence interval when you make those calculations. And remember that for any given confidence interval, the population mean either is or is not in that interval, which is to say it's wrong to say that there is a 95% chance that the population mean is within a given interval. In any particular calculation, it's either there or it's not. You can't really know whether it's there or not. So this is not Schrodinger's cat or whatever that weird quantum physics example is. It's not like a cat that's like 95% alive and 5% dead. No, it's either alive or dead. So the problem is that it's not totally knowable whether it's alive or dead, because you can't open the box. You just kind of say, well, if we did this right, most of the time it's going to be alive. So that's the point of the in-class example. If you tried this at home, maybe you got the population mean within your confidence interval, maybe you didn't. And that's a convenient case where we know what the population mean is, but in real life, when we're running linguistics experiments and applying statistics to them, we never find that out. We just kind of make the best educated guess that we can based on these assumptions we have about sort of normal distributions and the central limit theorem and whatnot. I'm not going to walk you through all those again, but hopefully this makes sense in terms of how to calculate a confidence interval. And just to make sure, I'm going to give you a homework assignment in which you do calculate a confidence interval. So we'll find out then for sure whether this got through. And if it hasn't gotten through yet, maybe you should watch this again before you try the homework. Okay, but that's all I'm going to say for now. Next time we'll get into sort of more sophisticated types of hypothesis testing building again on what we learned in this lecture and previous lectures as well. So I'll be looking forward to that because that's where things get really exciting. All right, see you then.